Okay, so we'll wait for 5 more minutes to see if anyone joins. Then we'll start sharp at 3:05. Okay, welcome back everyone. So this is NOC EE-62 NPTEL tutorials on basic electronics. The course is offered by Professor Mahesh P. Patil from IIT Bombay. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar here. So as you know, we are at the end of the 12-week session. So the duration of the course were 12 weeks. We went live for 3 to 5 p.m. every Sunday. This would be the last session of this tutorial course. So again, I would like to reiterate the basic prerequisites. You are expected to at least have gone through the previous week's lectures posted on the course web page, and also at least you must have attempted the assignments, right? I know that this assignment 12 solutions have been posted by NPTEL team on the course web page. So it will be helpful to those solutions were of online solutions, right? So I will try to explain the solutions in a little bit more depth. So regarding the decorum you should follow, please keep your microphones muted all the time. If you have any question, you can use the raise hand option, or you can ask if the number of participants are less, so you can unmute and ask your questions also. Also at the end of each topic and also at the end of the second hour, we will be given 10 to 15 minutes of time to ask your general query regarding the session. Okay. So for today's session, so far for last two sessions, we were dealing with digital circuits, sequential and combinational. So I think calculators were not that much necessary, but it is good to have a scientific calculator ready with you for today. Okay. So let's begin. This is week 12. So today we will be discussing basically analog to digital converters. In short, we call them ADCs, and also digital to analog converters. Here, digital and analog defines the nature of the signal. Okay. So I think you are familiar with the nature, what is analog and what is digital signals. So it would be helpful if you can unmute and tell me what do you mean by analog and what do you mean by digital. I think I have one participant. Karishma, if you can unmute and tell me what do you mean by analog and what do you mean by digital signals? Am I audible, by the way? G Charishma. I don't think you. Okay. Typically use only a few components and thus sorry. Typically use only a few components and are thus. No, no, I am not asking about analog circuits. You can unmute and speak up. Okay, it is better. It is not convenient for me to look at the chat. So you can just speak up your query. I was asking about what is analog signals and what are digital signals, not about the ICs or circuits. Those will those are secondary stuffs, right? We are talking about analog signals and digital signals. Actually, out lot of disturbance. Okay, no issue. So what I was asking about analog signals and digital signals, right? Okay, what is analog and digital here? You know, if you have a signal, let's say of this nature, right? V of t, and suppose you have t. Suppose you have a signal like this. So how do you get to have the signal like this? Most of the signals in nature, most of the signals in nature are of analog form, and analog means continuous in both time and its amplitude. Okay, that means it can take any value, or in another way to say that resolution of the signals is exactly zero, right? So now what about digital signals? So after analog signals, you have discrete time signals, right? Discrete time signals. What does that mean? You sample the time axis at certain interval and you record the value of the output at that point. Okay. So I would say if you sample the time axis, then you will get this. Okay. So this discrete time signals is you sampling the analog signal in time axis, in time sense, let me say time sense. Okay. So is that digital? Discrete time signals, are those signals called digital signals? Well, actually, they are not entirely called the digital signals because after this step is by the way called sampling. Okay. Then you need to do two more stages to convert it to digital signals. One is quantization. What does quantization do? Quantization does it samples the amplitude axis. Okay. Samples the amplitude axis. So it restricts the choice of amplitude of the signal. Okay. So again, you would see that you can have many number of quantized levels at the amplitude axis, but that is those if you have suppose 256 numbers of levels, right? So it is not convenient to work with 256 number of bits to represent 256 number of bits to represent each one bit for each level, right? So it is more convenient to encode it back, right? So at the next step, you have encoder, right? It encodes the signal, the quantized signal to some bits. Okay. And after that, you get your digital signals. Okay. So you see, you must have been studied this that digital signals are more convenient to work with because of its inherent properties, like immune to noise or regenerative repetition. So there are many things, and processing is much more easier. So digital signals are preferable over analog signals. But you see, this is your environment. Okay, let me, and also this is your environment, let's say, and you want to have your communication between these two places. So you will have your analog signals in the environment, right? Then in the middle, you will have your digital signal processors, DSPs. Okay, digital signal processor. Okay, because we know that digital signal processors are more convenient to use. At this level of the course, at the level of this course, I will not go deep into the what is DSP and how does DSP work or any mixed signal processor works. but basic steps I'll tell you that. So you see the input and output of a DSP is digital. Fine. So again, at the output you have analog signal at the environment. So you see there is a need for conversion of this analog stuff to digital, right? This analog stuff to digital. Again, this digital signal back to analog. Okay, so this is called your ADC or analog to digital converter. Analog to digital converter, and this is your DAC, right? Digital to analog converter. Okay, so you see when you will study for, you will go for higher studies or any industry, you will see find that suppose let me tell you, Bose you must have heard of, or Sony, the audio processors, the this headphones are of Sony's, right? This there are too many this analog to digital and digital to analog converters, right? And also some mixed signal converters. There are, you must have heard of this delta sigma converters also. So this kind of sophisticated stuff requires the basics knowledge of ADCs and DACs. That's why in this basic electronics course, you are reading about these things just to get familiarized about what is ADC and what is DAC. Okay. So, okay. So today we'll discuss about your ADCs and DACs. DACs later, let me discuss at a later stage. Okay. Let me start with ADCs, because the first few problems I will be dealing with are of ADCs. Okay, so I am giving you a pretext about what are the basic, very fundamental thing about ADCs. Most of the things you have covered in your lecture, it take it as a summary. Okay, analog to digital converters. So, what do you think that how analog to digital converter should be? What is the output and what is the input, right? So let me say this is my A to D block. Okay. So you should have a some voltage, analog voltage. Okay. You should have some analog voltage as an input. And what would be your output? Your output would be certain number of bits. Okay. Let's say this is your Dn, Dn minus 1. This is D1, and let's say this is D0. So okay, so what will we call this? We will call this as n bit ADC. Fine. So you see, a basic idea behind this is you have, suppose you have a Vmax, okay, and suppose you have a lowest voltage possible. Say you are not dealing with the negative voltage stuffs which we use in telecoms, right? We can in telecom systems you can use minus 48 volts, minus 12 volts also. You can carry those amount of voltages, right? So we are not talking about that. So in our ICs, let me say that 0 volt is the lowest value of the voltage we have. And now we want to design a 3-bit ADC. Okay. So for a 3-bit ADC, how so you need to suppose divide this range for how many times? For with 3 bits, you can create 8 levels, right? 2 to the power 3. So 1, 2, 3, 4, 5, 6, 7, 8. Let me just move the 0 to here. Okay. So now you say this is, suppose your some reference voltage is there, VR, and let me say some ground node is there. So let me say this is VR7, VR6, VR5, just random nomenclature. You just take it as a nomenclature on names. VR3, VR2, VR1. Okay. So what I'll assign that in this range, if my analog voltage is in this range, then what will be my output? My output will be 111. Okay. Similarly, 110, 100. Okay. So you see that if your input voltage or VA, suppose your VA lies at this point, okay, this is your VA level. So what will be the output of your ADC? Output of your ADC would be 100. Fine. So you have encoded or converted your analog signal of certain voltage to a digital form of digital bit stream of 100. So that is the main agenda of your ADC. So what do you think? What kind of components do you need to do this? One thing is that you need to constantly compare this VA with these voltages, right? This intermediate voltages. So you need some sort of comparators. Okay. So what are the comparators? You know that basic comparator you can just make it with a op-amp block. Okay, fine. So this is one kind of a comparator. Also, you see that, let me add one page. Also, you note that you have these voltages, right? You need to get these voltages somehow. So how to get these voltages? You need to have some voltage division stuff, right? Some resistive division, or let me rather say some voltage divider circuits, okay, to generate these intermediate levels. This VRIs, okay. So these are the basic concept that why we do need ADCs and what are ADCs mainly comprised of. So based on what how you make the ADCs, you can have many types of ADCs. In the lectures they have discussed. Let me just jot it down for you. Types of ADCs. Okay, in the lecture, Professor Patil has discussed these following types, right? The very common and popular type is flash type ADC, okay, which runs on parallel. But what is the disadvantage here? The disadvantage here is if you have gone through the lectures, so huge number of comparators are required, right? Huge number of comparators are required, okay. And also a very crucial point is that it can have some the comparators have some latency, or basically it creates some delay, okay. So the output may not, when the input changes, the output may not get converted out, the comparator may not give the output by that time. This will depend upon your let me say the slew rate of your op amp or some kind of that, those kind of metrics, right? So to avoid that, you need also some D flip-flop networks, D flip-flop chain, okay. So this is one kind. Another kind would be your very popular SADC. That's it. That is your successive approximation ADC. This is a more sophisticated type. Here, what you do, you use a DAC and you use a DAC and you use a comparator and connect the entire circuit back in a negative feedback. Okay. Details I will not be providing you because those are available on the lectures. So another type would be your dual slope integrated ADC. Okay. This is used basically for high precision. Some high precision, that means why do we need high precisions, by the way? We need high precisions in the cases where there are measurement equipments are involved, right? Instrumentation and measurements. So in those kind of applications, we need, let me just write it down, measurement applications, measurement equipments. Then you have this, let's say, digital ramp ADC. This was also discussed in the lecture. You can refer back. Also, you would have tracking ADC, right? These are very low cost and low speed operations. You use this, okay? And why low speed operations? And why does you have why do you have this low speed operations? You see, suppose for temperature sensors, right? Temperature in a room changes, it does not change very rapidly. Okay, temperature change is a very slow process. So to track those temperature changes, you need temperature sensors, which may not require those high precision or high speed ADCs. Fine. So, okay, so these are the ADCs. And for details, some of them I will discuss while solving the problem, but for in general details, look into the lectures. Okay. So let me start with the problem solving. So first thing is a 1 bit, a 10-bit successive approximation type ADC uses a clock frequency of 1 megahertz. What is the conversion time? First of all, what do you mean by conversion time? Conversion time is nothing but the time required from analog to digital conversion. Okay. So suppose you have a n bit and your conversion always may not be in a parallel way, right? Like flash ADC, where you have all the bits coming out at the same time. It may not be like that. So what do? You do it is in, suppose whenever you have some serial output of your bits, suppose you have n bits, okay, n bits output and serially out. Then you need to wait until unless your from LSB to MSB all the bits are out, all the bits are present. Okay, need to wait for arrival of all the bits from LSB to MSB at the output. Okay, so you know that your SADC is a successive approximation ADC, right? So it will not have your parallel operation wherever where in case of your flash ADC all the bits are out at the same time. So it's a very simple problem. So you have your clock frequency as 1 megahertz. Okay, what will be the clock period? So your clock period would be nothing but 1 over 1 megahertz, right? That is nothing but 1 microsecond. So in one clock period, you can have 1 bit of output, but your ADC is of, let me write it down, 1 clock period, you would have 1 bit output. But you need to wait for 10 bits. Fine. So what will be your conversion time? Net conversion time is nothing but your 10 into 1 microsecond because you have a 10-bit output. So your conversion time would be 10 microsecond. Fine. So your answer would be C. So this is very simple. Just you need to know the what is the type of your ADC, how the output are coming. It is coming sequentially one by one. So you need to have all your entire 10 bits to have a proper understanding of the input voltage, right? So that's why you have this total 10 microseconds of this conversion time. Okay, so let's move on to the next problem. The number of comparators which can be accommodated on a single chip with a specific IC technology is 600. Fine. What is the maximum number of bits possible for a flash type ADC made using this technology? Okay. What is fixed here? The number of comparators are fixed. Okay. So just let me draw a very basic. Okay. Okay. Let me say this is your some V reference. Okay. And this is, let me say this is my R by 2, this is R, and so this is R by 2. Okay, and you have your, this is your VA. Just do this. Okay, again this VA carries forward to this, and this you must have, if you have gone through the lectures, you must have seen that this is the kind of, this is the nature of your this, and this will be your this. These are the comparators. Okay, and these outputs are, let me say this is Cn minus 1, and this is C0. Okay, so these outputs, I'm not showing the D flip-flop chain. This is just a tentative diagram. This will again then be your fed to a logic circuit, or say some encoder. So you have your output. Okay, some number of bits. Okay, so if let me just, this is m minus 1, because I will be using n here, n minus 1, sorry, dn minus 1, dn minus 2, and d0. Okay, so if output is of n bits, you need 2 to the power n comparators. Okay, what is my comparator? Comparator is nothing but these blocks. Okay, so in your case, what is given? Given is 2 to the power n is equal to 600. Fine, that is fixed. So what would be your n? Your n would be log 600 base 2, that is 9.22. Fine. If you do this calculation, 2 to the power 9, you can also check that 2 to the power 9 is 512, and then you have some additional, right? So 600 log base 2 600 would be your 9.22. Fine. So what is the maximum number of possible bits of the output? Your lower floor, right, is your 9. 9 would be your maximum number of possible output bits. Okay. So your B is the right option. See, these are very pretty simple problem, right? So you just need to know what that for your n bits, 2 to the power n comparators are required. So 600 or 2 to the power n has been fixed. So using 600, I can take maximum 2 to the maximum 9-bit ADC, because for a 10-bit ADC you need 2 to the power 10, that is 1024 comparators, right? So 1024 comparators you will not have, you are not having. So your answer is 9. Fine. So let's move on to the next problem. This is also a similar. Here they have told that full scale for an ADC is 10 volt. That means your V max is 10 volt. Okay, 0 to 10. This thing, this they are telling to be 10 volt. It may not be 0, it may be some minus value to that. The difference should be 10 volt. So if the difference is 10 volt, and what is the resolution? The resolution is 5 millivolt. What is the resolution, by the way? This part is your resolution, this bin size. Okay, this is your resolution. So you can guess from this that how many numbers of comparator you can require. You just simply have to divide this by this resolution. Okay, so number of comparators required, 10 over 5 millivolt. That is nothing but your 2000. Okay, so for 5 millivolt resolution we need at least 2000 comparators. Okay, so 10 bit ADC gives us how many number of comparators? 1024, right? That is 2 to the power 10. So that is not sufficient. We can see that we need at least 2000, right? So we need to increase the bits, the size of the ADC. So 11 bit ADC gives us 2048 or 2 to the power 11 number of comparators. Fine. So what is the number of bits required? Number of bits required are 11. Okay. So your C would be the right answer. So let's move on to next problem. Okay. So a 10-bit DAC gives us an output of 2 VA equal to, okay, let me first tell you what a DAC is. Okay. Digital to analog converter. Fine. Now it is just the opposite of your ADC. Fine. Here you have some n bits as input, and you will have a VA or some analog voltage. Okay. To define that, let me make it a function of time. This is your DA converter. And let me have some V reference voltage here also and some ground node. Fine. So if you have gone through the lectures, you know that two types of DACs have been discussed in the lecture. One would be weighted binary resistors DAC, and another type R2R ladder. This is very popular actually, ladder type DACs. Okay. When you were going through the lectures, I am sure that you have found out that your ADCs are more difficult uh, to study than your DACs, right? And this is actually quite true because in practice also ADCs are quite more tedious to build than DACs. So these two types were discussed in the class. So what basically a DAC do? Suppose you have a this four blocks. Let me just take four blocks. Okay, S0, S1, S2, S3. Okay, and you have some VA. So how will the output look like? Output will look like something like this. Output will look like something like this. Okay, your this will be your K. And K is anything but is K is you can take it. It is proportional to your VR or the reference voltage, or you can take it as the resolution, right? Let me just write down the formula first. Then your S2 into 2 square plus S1 into 2 to the power 1 plus S0 into 2 to the power 0. Here S3, S2, S1 and S0 belongs to a set of 0 and 1. It can be either 0 or either 1, right? Just as the binary form. Your digital nature are zeros and ones only, right? And your K is here. K you can say the resolution, or it is proportional to your VR. Okay. And how K is the resolution? Because if you just this is your LSB, right? S0 is your LSB. If you change your LSB and take the difference, then you will get your resolution. See, whenever this is 0, this entire keeping this entire part same, if my S0 is 0 and again S0 is 1, it will give me a difference of 1 only, and that is multiplied to K is nothing but your K only, right? So that is why your K is the resolution here. Or let me just write it down that VA1, one case it would be K into S3 2 to the power 3 plus S2 2 to the power 2 plus S1 2 to the power 1 plus let me take S0 equal to 1 and 2 to the power 0 is 1, so it is 1, right? And VA2 S3 2 to the power 3 plus S2 2 to the power 2 S1 2 to the power 1 plus if S0 is 0, then it is 0. Okay. So your delta V or resolution is your VA1 minus VA2 is nothing but K. Okay. So that's how this comes about. Okay. Now the question is that 10-bit ADC gives an output of VA equal to 2.5 for an input of this. Okay. So you see this would be your S9, S8, S7 and so on. This would be S0, fine, because it is a 10-bit and we start with 0 by the way. So you have only your 8th bit 1. Fine. So 2 to the power 8 will be there only. So your VA is equal to K into S9 into 2 to the power 9 plus S8 into 2 to the power 8, S7 into 2 to the power 7 plus S0 into 2 to the power 0. So from the question it is 2.5 volt, 2.5 volt, and only your S8 is 1, else everything is this 0 and everything is 0. Okay, so you have only this is 1, so 2 to the power 8 will only be there. Fine. So what would be your K or resolution is your 2.5 volt divided by 2 to the power 8, and the answer comes out to be 9.76 millivolt. Fine. So your answer would be A. Okay. In this way, you can solve the problem for this kind of nature, right? So next, again, the DAC of question 4. That means 10-bit DAC I am having. So this is my S8, S7, 6, 5. This is 4. This is 3. This is 2. Fine. And here also 8, 7, and this should be 0, 1, 2, 3. Okay, so your VA1 is nothing but K into, here is this, all these are only ones. Fine. So you have 2 to the power 8 plus 2 to the power 7 plus 2 raised to 4 plus 2 raised to 3. Fine. And your VA2 would be K times only the SS which has the value of 1 will be there. So it will be 2 raised to 8, 2 raised to 7 plus 2 raised to 3. Okay, and here I have 2 raised to 2 also. So what is your VA1 minus VA2? K times this cancels, this cancels, this cancels. So we have only 2 to the power 4 plus 2 square. Okay, K was found out to be 9.76 millivolt into, you have this 16 and 4, right? 20. So your output will be 0.195 volt. Fine. So D would be your right answer. Okay. So moving on to problem number 6. For the DAC of question 4, what is VA corresponding to the this input? Okay. Let me first identify what are the ones here. Ninth bit, then 8, 7, 6th bit, then 5th bit, then this is 2, this is 1. Okay. So your VA here would be K times 2 to the power 9 plus 2 to the power 6, 5, 2 and 1. Okay, so it is your 9.76 millivolt into, this is your 512, 64, 32 plus 4 plus 1, 4 plus 2. Okay, so this you will have this into 614, because this 64 plus 36 would be your just, this is your 96, this is your 6, so 102, so it will be 614, right? So the value would be 5.992 volt. Okay, if you just compute it, the value would come out to be this. So your output will be C. Fine. So these are pretty simple problems, right? Just basic arithmetics. Okay, so next going to the problem number 7. What do we have here? What type of ADC is generally used in a digital voltmeter? Fine. So what is my digital voltmeter? Digital voltmeter is a measuring equipment, right? What do we need? We need high precision, and that means we can use dual slope integrating type ADC, right? So your D would be the right answer. This we have discussed earlier also. Fine. Uh, just let me look through. Yeah. So this was the thing, right? Dual slope integrating type, high precision measuring equipment. We will discuss about dual slope, by the way, in a later problem. Okay. So that's all for so far. And let me ask you if you have any question, or else I'll take a very short 5 minute break. You can ask your question in the meantime. Okay. So we have been discussing this ADCs. Okay. So we have discussed so far what are analog and digital signals. Then we have discussed what is a basic ADC, how does a basic ADC look like, and by intuition, we have seen that what are the basic components that should be required in making a ADC, making an ADC. And then we also discussed briefly the names of the ADCs which were discussed in the class. For details, you are obviously required to look into the lecture videos. Okay, here we have mentioned that flash type ADCs provides you parallel output, right? That means all the bits come at the same time. Successive approximation ADC, it provides you a sequential output. Okay, so until unless all the bits are arrived, you cannot consider it, the conversion is done. Then we have named the dual slope integrating type ADC. This is used for high precision, so mainly used in the measuring equipments. Then we have discussed about digital ramp ADCs. Okay, we have not discussed, we have just named. Then we have named tracking ADC. Tracking ADCs are generally of very low cost and low speed. So the processes which are slow, suppose your temperature sensors or suppose your strain gauge system, right? Those things you can use in this type of tracking ADCs. Why to spend more penny when this tracking ADC can do the job, right? So then we have we have driven to the problems. So first we have seen what is the conversion time. Then, as I have mentioned earlier also, that for SA type ADC, you have to wait for all the bits to arrive at the output. So in this way you can compute your net conversion time. That will be nothing but your total number of bits multiplied by number of time periods, the total period of the one clock period. Okay, so net conversion rate will be one clock period times how many number of bits are there in the ADC. Okay, so next problem we have discussed about that for a kind of flash ADC, how many number of comparators are required. We have seen that this is the most important point, that for an n-bit ADC, we need 2 to the power n number of comparators. Okay. Then you just simply compute the how many number of comparators are required and what are the number of bits required for a given number of comparators. Okay. So then again we have discussed what is called resolution and how you can get the number of comparators, and also what is the number of bits required once you know the number of comparators required. Then we have discussed briefly about DACs and how a normal, this is a DAC, okay, and how the output of the voltage looks, output analog voltage looks like, and also what is the resolution here. This K terms defines the resolution, and how to, why it is called resolution, because when your LSB is changed from 0 to 1, then you can take the difference and you will get that this amount of voltage is the minimum difference you can measure, right? That is called the resolution. So for the given problem, we needed to find out the resolution, so we have done that. Then for the next problem, again the DAC output, DAC input are given, and for two inputs we need to find out the difference. We already knew the K value from last problem, K from last problem. Okay, so we have calculated this, and then we had to find out for a particular combination of input what is the output voltage, analog voltage. So this we have calculated. Also, again, the question was that in a digital voltmeter, what kind of ADC is generally used, right? So we see that due to its high precision, dual slope integrating type ADCs are used. Okay. So now let's move on. So problem number 8, it is asked that the circuit shown in the figure is DAC with input this S3, S2, S1, S0 connected to the op-amp virtual ground. If that means this connection will make, if your this A3, sorry, if your S3 is 1, okay, and if your this connection will make if S3 equal to 0, okay, either it will be connected to ground or it will be connected to virtual ground, okay. So how to solve this kind of circuits, okay? If you see clearly, this is nothing but your R2R ladder type DAC, okay. So this you must have gone through in the lecture. So let me just draw an equivalent. So let me do it step by step. What I desire is to make the circuit in this form, okay. My desire is to, because this form we can handle pretty well, right? We have been solving this kind of negative feedback op-amp circuits for a very long time. So this is your RTH set, some Thevenin resistance, and this is your, let's say, some VTH, okay. This is your output, fine. So we want to find out this entire stuff to this a series Thevenin voltage and Thevenin resistance. Okay, so we need to find out the Thevenin resistance and Thevenin voltage. How do you do that? So Thevenin resistance or RTH. Fine. The way you find out Thevenin resistance is as follows. These two are, okay, I am drawing here. Then these two are I am drawing here. Then this R I am drawing here. Then this 2R, R, 2R, R, and finally another 2R. Okay. So we needed to find out my RTH at this point. Okay. So how do I find out my RTH? The way to do it is, you notice that these are in parallel, right? So it will be R. This R and this R will be in series. So it will be 2R. So there will be again this parallel 2R. So this again will convert it to R. Okay, it will again be 2R, then 2R, 2R, R, R, 2R, and finally you will have a resistance parallel here 2R. So upon solving this, you will get R. So your RTH is nothing but R. It is pretty simple to see, okay? Now, what about the Thevenin voltage? You can draw the circuit, complete circuit in this fashion, okay? This is so we had this, okay? So this would be your A0. So S0 VR, S1 VR, S2 VR, S3 VR, okay? And we want to find out the VTH. This would be 2R, 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 is R. Okay. So what do? You see that this is a first thing observation, linear network. Okay. Use superposition. That means first I will take this and null all the other sources. Okay. So step one, I will just have this 2R. This is 0VR. This is 2R. Then I'll have this network. Okay. So this would be your R, 2R, R, 2R, R, 2R. Okay. So how to get the Thevenin voltage at this VTH1, say? What is VTH1? So VTH1, how can you solve it? You can solve it in this fashion. Okay. First, you consider this much of the network. Okay. Now, if we use Thevenin theorem here, you can easily convert this to a series resistance with a R. Okay. And then your remaining network would be of P. So this would be your remaining network. Fine. So what is your Thevenin resistance at this between this node? You null this and check two are parallel. So Thevenin resistance would be RTH equals to nothing but R. Okay. So I will not write RTH here. I will simply write R. And what about this voltage? This is the Thevenin voltage. What about this Thevenin voltage? This is nothing but a series current will flow here and division, voltage division will occur, right? Between 2R and 2R resistances. So this voltage will be S0 VR by 2. Fine. So now if I take this much of the circuit, okay, and apply Thevenin theorem looking at this port, what will I find? From this step to this, from this step to next step, applying Thevenin. Okay. So again, I will have what? A series resistance, a series voltage source, Thevenin voltage with a series resistance. Fine. And then I will have this network. Fine. Again, you can see that this is nothing but this I can just remove and write it as 2R. Okay. Same stuff. This will be grounded. So from this node, this 2R will be in parallel. So this will be your R and this will be, this voltage will be S0 VR by 2 divided by 2, right? That is nothing but S0 VR by 4. Fine. So again, if we take this much of the circuit and apply Thevenin, now you can directly tell me that your circuit will nothing but simply look like this. Okay. So your this portion is this one and this is this and you have this network. Okay. So this is your R, this is your 2R and this will be your R and this will be S0 VR by 8. Fine. Similarly, again if you do that, you will have a finally you will have a S0 VR by 16 and a series resistance of R. Fine. This is for what? This is for only this source. Now similarly if you do for this and this and use superposition, what will you get at the final VTH? This is your nothing but VTH1. Okay. Similarly your VTH would be S0 VR by 16 plus S. You can check this. Similarly S1 VR by 8, S2 VR by 4, S3 VR by 2. Okay. So your VTH would be, if you take this common, SR by VR by 16, if you take common, it would be S0 into 2 to the power 0, S1 into 2 to the power 1, S2 into 2 to 2 square plus S3 into 2 cube. Okay. So this is your VTH. Now what were the circuit? This was your circuit, right? We wanted to find this. Okay. Just copy it and if you paste it here, fine. So what do you have? You have this as R. This VTH is nothing but this value. So what is your V naught? From the op-amp circuit, you can see that from op-amp circuit, we note V naught is nothing but minus 2R by RTH into VTH. That is nothing but minus 2 into VTH. And what is my VTH? Minus 2 VR by 16 into S0 2 to the power 0, S1 2 to the power 1, S2 2 to the power 2 plus S3 2 to the power 3. Fine. Now what was the question? The question was that for this value, what is V0, right? 1001. Okay. So your S3 is 1, S2 is 0, S1 is 0, S0 is 1. Okay. So what would be my V0? V0 will be nothing but minus 2 into VR by 16. This is 1 and this is 1. This will be 0. So you have 2 to the power 3 plus 1. So you will have this 9 into 2. So 9 by 8 into VR. Okay. So your output, you will get it to be, what is your 9 by 8? Your 9 by 8, you will find it out to be minus 1.125 VR. Okay. So this would be your answer. So C would be your right answer. Okay. So again, moving on to the next problem. In the similar manner, you can do what? Here your S3 is 0, S2 is 1, S1 is 1, and S0 is 0, right? So what is your V out? Minus, we have, what did you see? Minus 2 VR by 16 into, in this case, we will have only this term and this term, right? So we will have 2 plus 2 square. So that is your minus VR by 8 into your 4 plus 2, 6. Okay, minus 3 by 4 VR, or that would be minus 0.75 VR. Okay, so your answer would be B. Fine. So in this way, you can solve this kind of problem. This is just the crux is to note that the DAC is deploying a R2R ladder. Okay, that is the main point to note. Rest of the analysis are very simple. So let's move on to the next problem. So consider a 8-bit dual slope ADC with a clock period of 1 millisecond. What is the worst case conversion time, right? Conversion time, we know the time required for an analog input to be a digital output. Okay. So let me discuss briefly about dual slope integrating type ADC. You will see why how the name has come about. So the heart at this type of circuit, this type of ADC is an integrator. Okay. So first, let me make one integrator. Just let me add one more page. How do you make an integrator? Remember, you have resistance, you have this capacitance. Okay, so this is your integrator. Let's call it Vi. Let's call it Vo. Okay, so now let us have a switch here. Okay, so this is your, let's say, Va. Let's say this is your Vr. Okay, the type of switch would be, let's say, single pole double through. Okay, SPDT type of switch. So again, this V out you need to compare with something. Fine. So let me draw the comparator in this fashion. You will get to see how why I have been making this circuit like this. I have a AND gate, I have a clock pulse here, then say I have a counter. This the number of bits of the counter determines what is the your what how many bits of your ADC can handle. Okay, so it is a n bit counter, let's say. And then you put this output, let's say this is overflow bit to this SPDT. Okay, so this is the kind of stuff you are having in a dual slope ADC. So how does this work? Let me explain. So just for the sake of it, let me mark that this is an integrator block, fine, and this is a comparator block. Comparator integrator. Okay, and also for flexibility, let me add a switch here. Okay, so how does this work? Let me just draw a plot. So let's say this is your VA, and let's say this is your VR. This is your T1, this duration is T2, and let's say this is your minus VR. Okay, so what is your V naught? V naught is this point, it's nothing but minus 1 by RC integration. This is your input VI, so VIT. Okay, this is an integrator block. So this is your VIT. Okay, this is T, and let's say this is your VOT. This is T. Okay, so what is the working mechanism here? At t equal to 0 minus, that means this is 0, let's say 0 minus, close the switch S momentarily. Okay, what does that do? If you close this switch, that means this and this are shorted. This is in virtual ground, this node is in virtual ground because of negative feedback, so your V out will be at 0. Okay, this makes your V out at 0. That means this at 0 you have 0 voltage here. Fine. Now open S and VI equal to VA for a time of T1. Okay. So if this switch is now open, so it will act just like a normal integrator circuit. Now, if you make this connection, okay, so VI equal to, what will happen? VI equal to your VA, fine. And what will that make? And my V out will be, V out trend is shown here. Okay, V out will be something like this. A step signal is integrated and become a ramp signal, and the slope will be VA by RC. Fine. From this equation, you can write that the slope will be VA by RC. Fine. This is your T1, and let's say this duration is your T1 plus T2. Okay. So now what you do? Now at T equal to T1, switch the SPDT from VA to VR. Okay. So your VI has become minus of VR, and we take mod VR greater than VA. Okay. What does that do? And let it be there until V out is equal to 0. That means at this point your output starts and become like this. Okay. The slope will be VR by RC. Or rather, let me say mod VR by RC. Fine. So now how does the counter come into picture? Okay. So you see your V, whenever for a certain time period T1 plus T2, you have a non-zero V out. Okay. That means your V out is less than 0. So I need to compare this circuit to get a time period. Okay. So I use a comparator to see when minus V naught is more than 0. Okay. That is what has been achieved by this comparator. So whenever this is whenever, so for 0 less than t less than t1 plus t2, I will have, let's say this input is your Vx. I will have Vx equal to 1. Okay. So one input of my AND gate will be 1 always during that time. Fine. So as clock comes in, counter starts counting. Okay. So it counts till, and also you can note from this side that these ratios, that is your VA into T1 is equal to mod VR into T2, right? So you can find out that your T2 is to be T1 by mod VR into VA. Okay. So I what do I need? I need to convert these to some digital stream, right? What have I done? I have converted this VA to T2, right? Some time duration. Now I will convert this T2 to some I will convert this T2 to some bit stream. Okay. So how do you do that? First, let me just tell this. So the counter, it counts till 2 to the power n and makes overflow 1. Okay. As soon as my overflow is 1, what does it do? It changes the SPDT switch to Vi equal to Vr. Okay. Or minus Vr. And resets the counter. Fine. So now when my output is at that stage, my counter is reset and it will start fresh count. Okay. It will start fresh count till my output is going back to 0. Okay. That means in this duration, let me just, how do I show that? Okay. Star. Okay. During output from, let me say this is some minus V1, from minus V1 to 0, counter counts and gives an estimate of T2. Okay. So T2 converted to some n bit stream. Okay. So what was my T2? My T2 was T1 by mod VR into VA equal to some bit stream. Okay. Now, if this is known and this is known, so can I say that my VA has converted to some bit stream? These are known. Okay. So in this way, your VA has converted to some digital bit stream. Okay. This is how this ADC works. Okay. Why does it call dual slope? Because this slope and this slope are not same. This slope is much more steeper. Okay. So this is why it is called a dual slope ADC. Now the question is, what is the worst case conversion time? Okay. So you see, for worst case, my T1 should be equal to T2. Then on, if T1, if this is stretched to T2, then whatever time my T1 takes and T2 will take the same amount of time to get back to 0. So I have a maximum delay or maximum conversion time from analog to digital, analog input to digital output. Okay. So what was my this clock frequency? Clock period is 8 millisecond, right? Clock period is 8 millisecond. Okay. And how many number of counting it will be there? 8-bit counter will count. Clock period was 1 millisecond, right? Not 8 milliseconds. 8-bit counter will count 256 numbers. Okay. So what will be my T1? You see, when 0 to T1, the counter counts 2 to the power n. Okay. So T1 would be nothing but my 1 millisecond into 256. That is 256 millisecond. Okay. So what would be T2? T2 will be also same for worst case 256 millisecond. And what is the conversion time? It is nothing but T1 plus T2 512 millisecond. Okay. So your answer would be 512 millisecond. So the logic behind this, it is that whenever your input is there, analog signal is there, whenever your input analog signal is there, it will integrate it for a duration of T1, and during that T1 duration, this counter will start counting, and it will it will count to how much time? It will count to the maximum value possible, because until unless it has counted 2 to the power n, the overflow will not be 1. So this remains 1, and the clock pulses keeps on coming. The clock pulses are like this. So the clock pulses keeps on coming, and your this up counter starts counting. It will count to 2 to the power n, and once it 2 to the power n is reached, then this overflow bit will make this SPDT switch from VA to VR. Okay. So as soon as it switches from VA to VR, fine. Then at that instant my counter is reset. Fine. And also what happens that this integrating action will take place, and it will go back to 0. And once it will go back to 0, during how much time it will take? It will take this T2 amount of time. So this T2 amount of time, again this counter will start counting up, right? So but now it will not count up to 2 to the power n. Why? Because this slope is much steeper. It will count much, the change will be much sharper, so it will not be able to count 2 to the power n. So the count will always be 2 to the less than 2 to the power n for T2. That's why this is the reason why we have taken that this mod VR is much greater than mod VR is greater than VA. Okay. So what is the worst case? When this mod VR is equal to VA, then I have in T2 duration also I will have 2 to the power n count. Fine. So 2 to the power n count requires 2 to the power n into 1 clock period. Okay. So that's what we have done. 2 to the power 8 into 1 clock period. That is one for the this cycle, and for this up cycle also. For T2, we will have the similar amount of time. So that is why it is called the worst case. So in other words, worst case also can be defined by VA equal to mod VR. Okay. These are the same conditions. Sorry, this and this, not this and this. This and this are the same condition. Okay. So this is how your dual slope ADCs work. So next problem is, consider a 6-bit weighted register DAC. Let R5 correspond to the MSB and R0 correspond to LSB. So what is R5 by R0? Okay. So just let me draw a weighted bridged DAC. Okay. So your weighted bridge DAC would be something like this. You have 6 bit, right? So you will have 6 switches. Okay, you will have this kind of connections. So let me just connect these things. Okay, so and your ground wire will be something like this. Okay, so this is where you have your VR, and now you have your resistors. This is, let's say, A0, A1, A2, A3, A4, A5. Okay, and these all are connected, and this is fed to a inverting amplifier. Okay, this is your RF. Okay, this is your V out. Generally, the binary weighted resistors, the resistances are like that. This is your R5 would be R, R4 would be 2R, R3 would be 4R, R4 would be 8R, R5 would be, sorry, R2, this would be R1, 16R, and R0 would be 32R. Okay, so this is the diagram of your a binary 6-bit weighted resistor DAC. Okay, so your R5 is R, R0 is 32R. Okay, so what is your R5 by R0? Is nothing but your 1 over 32. Okay, so I think the answer is invertedly given. So B would be your right answer. Okay, so fine. Let's move on to the next problem. In the DSC of question 11, the same one. If R F is R, okay, and this is this, okay. So what do we do now? We have to just compute this currents, okay. This this current is the same current. So what are the currents? So your VR one current is here coming, these currents will be adding up. Okay, so what is this voltage? This voltage we can assume it to be S5 times VR. Okay, and you can assume it to be S4 times VR, S3 times VR, S2 times VR. And why does why am I writing it in that sense? Is that when your S5 is 1, that means when your A5 S5 is 1, that means this network, this switch will be forming. Okay. When S5 is 0, then obviously this ground switch will be forming. This is S1 into VR. This is S0 into VR. Okay. So what are the total currents? S5 into VR by R plus S4 into VR by 2R, S3 VR by 4R, S4, sorry, S2 VR by 8R, S1 VR by 16R, and your S0 VR by 32R. Okay, that should be equal to minus this current, right? Minus V0 by RF. Fine. So what do we have here? If we take VR by let's say 32 R common, so I have S5 into 2 to the power 5 plus S4 into 2 to the power 4, 2 to the power 3, S2 into 2 square, S1 into 2 raised to 1 plus S0 into 2 raised to 0, that is equal to minus V0 by RF. Fine. So what is the output voltage? So V0 is equal to VR into RF by minus this divide by 32R into this stuff. Just let me remove it and copy this. Okay, so this is the value. So what do I have? I have S5 is 1 and S2 is 1. Okay, so I have V0 equal to minus, what is my VR? Minus 5 into RF is R by 32 into R, and what will I have? I have this 2 to the power 5 plus this 2 square, right? So I have this cancel. This will be 36. So 5 into 36 by 32. It is 5 into 9 by 8. That is 45 by 8. 5.625 volt. Okay. So D would be my right answer. Again, moving on to the next problem. So in the DAC of Q12, suppose all the resistors including RF has a 2% tolerance. Okay. So what is the maximum output voltage for this? So how can I calculate that? The way to calculate that is, you see your V out is nothing but your minus VR by 32R into RF into this bracket quantity. Okay. So if my RF is, if RF has a 2% tolerance. Okay, so let me do it in another way. So for V naught to be maximum, RF needs to be maximum and R needs to remain minimum. Okay, so what is RF maximum? Nominal value R into 1.02, because I have a 2% tolerance. And what is R? R would be this R into 0.98, this R. So I have a tolerance of that also. So what will I have? I have V0 equal to, this sequence is the same. So I have V0 equals to V0 nominal into 1.02 over 0.98. Fine. That will be your 5.625 into 1.02 over 0.98 volt. Fine. What is the value? The value will come out to be 5.855 volt. Okay. So C is your right option. How did we do that? We simply used the very fundamental phenomena that if any quantity or any ratio is to be maximum, the denominator has to be minimum and the numerator has to be maximum, right? The same philosophy we have used here, and only term which is changing with tolerance is this and this, right? So I have this, let's say this is R0, R0 is a nominal value. Let R0 be the nominal value, okay? Then it is simply just a matter of manipulation. So moving on to problem number 14, the same question. Now they want us to find the minimum output voltage. Okay. Similarly, my V out will be what? V naught nominal into 0.98 by 1.02. On the same logic what we have used in the last case. So that would be 5.625 into 0.98 by 1.02. That is nothing but your 5.404 volt. Okay. So in this way you can solve the problems. Okay. So okay, I think that's all I have for today. So let me just again tell you what we have done. So till 7th, I have already provided a brief recap earlier also. So I will again go from problem number 8. So in problem number 8, what did we study? We studied that what is my basic R2R type ladder R2R ladder type DACs. We have tried to find out how to analyze the Thevenin resistance and Thevenin voltages in detail, step by step manner. Okay, so we could calculate the output voltage for any combination of input, digital input, right? So we have found out this. Okay, next on the same problem for a different type of combination, we have find out the output voltage. The main key crux of this thing is that you need to understand that DAC is nothing but a R2R ladder type. Okay. Then moving on to problem number 10, we have discussed in detail how the dual slope integrating type ADC works and what is the worst case. Worst case means this VA and VR are of the same amplitude. Then this T1 and T2 will also be of the same value. Fine. So after upon analysis, we have seen that 512 millisecond is the net conversion time. Okay. So again, consider a 6-bit in problem number 11. We have discussed how a 6-bit weighted register DAC looks like and what is the mode of functionality. And we had to calculate some basic parameters like what is the ratio of two resistances of MSB and LSB. And then in the next problem, we have discussed that for a particular input, what will be my output, right? So we have just simplified that. We see that this is nothing but the all the currents will come and add in that this node, and it will flow through this RF. Okay, this is nothing but an inverting amplifier in a negative feedback. So we have calculated this output, and then we have to calculate what if the resistances have some tolerances, right? In the real life scenario, you will not find, if suppose you want to buy a 1K resistance from the market, okay? If you come and measure the resistances, you will see that there will be a plus minus 5% or 2% tolerances. Also, if you see the resistance, the color bands on the resistance, the color coding of the resistance, you will see that there are two color at the end is been assigned for this tolerance limit, okay, so that these resistances are can vary, can have a acceptable variation about the nominal value, okay. So similarly we have calculated this case. Once we have to calculate the what is the output, maximum output, and once we have to calculate what is the minimum output, okay. So that's all from my side. I think we are at the end of the course. So it has been a very good experience for me. So I think you have an exam on 30th April, I guess. Please confirm the date with the mail and the NPTEL team, and also it will be given in the portal. Okay. So all the best for your exams. Okay. Thank you.